I'm going to hand off the presentation to Michael Gray, who's a lead engineer here at Venable Instruments and actually has been at Venable longer than anyone else. He worked with Dean Venable. So Mike's a great resource, tons of knowledge. And Mike, I'm going to hand it off.
All righty, I'll get started on this. We'll talk about our bread and butter, stabilizing power supply control loops, and also measuring source and load impedance. And if there is enough time, we'll talk about conducted susceptibility too. Okay, let's see. Okay, now my now it's all frozen. Okay. Let's try that. Okay. Here's our instrument. This is our 3-channel unit. It's a Venable 350C. Um, we also have 2 and 4-channel units available. The channel or the channels and the generator are all isolated to 600 volts from ground. So in many cases, you do not need to use an injection transformer to inject into a live circuit. The channel ranges go from 10 millivolts to 500 volts peak, so they'll pretty much handle anything you can throw at them. Plus, you can add high voltage probes if you need to go higher than that. And the interface is that we use to talk to it are originally the US or the GPIB IEEE 488, and lately we've been using the USB 2.0. The other part of our system is our software. So our new software is Python based, which makes it platform dependent. It'll pretty much run on any of the newer Windows 7 to 11. This software uses a Windows WinUSB software driver, so you don't have to fool around with loading drivers for our instrument. So everything's built into Windows now. We use this software to control and uh, plot the data. And here's a screenshot of our software, our new software. And to the right, you will see the readings. This gives you the readings from the channels and voltage and gain and phase. Then we have the analyzer control menu. Oops. Analyzer control menu, which is used to control the analyzer by setting the start-stop frequencies of sweep, injection levels, DC offset. You can also increase or shorten the integration time or integration cycles depending on which frequencies you're measuring at. In the center, we have our plot. Over to our left, we have our navigation bar that you can put multiple tab plots in one file, and the navigation bar helps you keep track of them. And then we have our math menu, where you can do transfer function math like multiply, add, divide, the plots on the screen. And at the bottom, we have the command display, which just shows the communication between the instrument and the software. And not shown is the analyzer control menu, or I mean the synthesis circuit analysis menu, which we use to design error amplifier for our feedback circuit. So I guess I'll start with the loop gain measurements. We have stability criteria. Now our Bodie plot is not a standard Bodie plot a lot. Even I was taught in school to measure the phase margin from the minus 180-degree phase shift line, uh, and the gain margin too. But all of our gain margin and phase margins are measured from the 0-degree line, basically. And that's because in the negative sign drops out of the loop gain, basically, when you do your closed loop gain math, but the loop gain is actually negative. So there's already a minus 180 degrees phase shift. So that's why our plots will begin at plus or minus 180 and or more phase shift, and then go down to 360 or 0 degrees. However, this makes it a lot easier this way. This method, or the way we present the data, is it's a lot easier to read the phase and gain margin. So the way we do measure the gain, the open loop gain, is by finding a place in the circuit where we can break the loop, but still leave the loop closed. So here we have two injection points. The one on the left is probably the least favorable, mainly because the output impedance of op amps usually rises with frequency. The one on the right, the other injection point, is at the top of the resistor divider string on the error amplifier connected to the output of the power supply. This usually provides the best plot spot, and we usually will put a injection resistor between the output of the power supply and the resistor divider string. That can be a resistor anywhere from 10 to 100 ohms. It depends on if you want how much that resistor will affect the set point of your power supply. So when we measure loop gain with the loop close, we're using the method developed by Dr. David Middlebrook, where we find a path where the feedback loop is confined to a single place. There can't be any parallel paths around that point, and a low impedance is driving into a high impedance. So typically that good spot is the output of the power supply, where the loop goes into the resistor divider string of the switching mode power supply. So this is how we would hook up to measure the feedback loop. We're basically it's connecting our oscillator across the injection resistor, and then placing channel 1 on the error amplifier side, or the input side of the loop, and channel 2 on the output side of the power supply loop, and then injecting there, and that will give us the entire feedback loop. And in this picture, there's an extra channel, so you can hook the extra channel to the output of the error amplifier, and that allows you to measure all of the different transfer functions in the loop, such as the error amplifier or the modulator. And we're mostly concerned with the modulator, since we want to design an error amplifier to compensate it. If you only have two channels, you could just move, say, channel 2 over to where channel 3 is connected, and that'll allow you to measure the error amplifier. Or you can move channel 1 to where the error amplifier point is, and that would give you the transfer function of the power stage or modulator. So once you find the correct injection point, you can measure any transfer function in that loop. And we'll start with a loop design. This is a eval board from TI. It's a synchronous buck with a transconductance amplifier. And to your right, you'll see the output. R7 is the injection resistor. This is the one we would be injecting across. So we would connect our oscillator between test point 7 and test point 8 to inject there, and then hook channel 2 from test point 8 to ground, and then and connect channel 1 from test point 7 to ground, and that would give us our entire feedback loop. And if we want to measure the power stage, we would move like channel 1 to the comp pin, and that would give us the controlled output or modulator transfer function for this circuit. When we're injecting, we usually inject from a low frequency. I selected 10 here. It just depends on how high the gain gets. And the stop frequency is the switching frequency. In this in this in this case, since we're not using a injection transformer, I'm only injecting about 40 millivolts into this circuit. That's basically the 40 millivolts is because it's when we're doing these type of measurements, they're small signal measurements is what they are. So you do not need to inject much signal. If you inject too much, you will get a very you'll introduce non-linearities and clipping, and you will get bad results in your feedback plot. So I would, and then you could also set your integration time. Here it's set to 1. I usually recommend about 3 seconds if you want to get a nice smooth plot without any noise. You can also use the servo. I'm just not going to get into that. There's really not enough time, but that's a good method of injecting a signal into the loop. And we actually have a blog post on our website on how to use a servo to inject signals. But it's basically you're fixing a voltage on one channel, such this one says channel 1. If I click the servo on, it would try to drive channel 1 to 20 millivolts. But we might discuss that at another time, or somebody, you can ask questions, and I can get you a link to the blog post on how to set up a servo for measurements. And this is a complete open loop gain plot. It's running from 10 to 480 kilohertz. The crossover frequency is around 30 kilohertz, and the phase margin is about 60 degrees. Next, here's our modulator controlled output Bode plot. So I'm measuring from the comp pin to the output of the power supply. And this is a peak current mode control type power supply. So the roll off is about one slope, or 20 dB per decade. And what I want to do is I'm selecting a crossover point or crossover frequency for the loop bandwidth. And here I've selected 30 kilohertz as my crossover point. And I will import the gain and the phase at this crossover point into our software. So yeah, talked about that. Measure the controlled output. And I'm going to set this to 30 kilohertz and a phase margin of 60 degrees. And There's a reason for that because I'm going to use a type 2. I might need to use a type 3 if I wanted a higher phase margin, but I'm just going to select the 60 for now. Okay, this is the measurement of the gain. So we are going to invert that measurement, or our software is to get the gain we're looking for in our error amplifier at the crossover point. And the same thing here, we are going to figure out how much phase boost or phase light, I guess it's phase lead that we need at the crossover to achieve that phase margin. And graphically, this is what we're doing. We're taking these two gains, inverting the compensation to get a 0 dB crossover. The same with the phase of the oh, the phase at the crossover and the phase of the compensator to give the phase margin that we're looking for. Um, and here's a look at our circuit analysis and synthesis menu. And what I do is I would import the value. I import the values. I can use a slide bar cursor and import the values into this first window in this menu. So I selected 30 kilohertz. I typed in my desired phase margin, and then these are the measurements at 30 kilohertz of the measurement in dB gain and phase shift at 30 kilohertz of our control to output function. To the lower left, we have the circuit topology, is what I call it. And there's three types of amplifiers. There's type 1, type 2, and type 3. Type 1 is just basically an integrator. Type 2 is an integrator with a low frequency 0 and a high frequency pole. And a type 3 is an integrator with the two low frequency zeros and two high frequency poles to give you even more, as we call it, phase boost or phase lead to the circuit. So I am selecting a type 2, which is the simplest one that allows you to control the phase margin. Circuit inverting is the default. There are some feedback networks where you need a positive error amplifier, but this isn't one. The amplifier is a transconductance. At my top of my resistor divider string, I've got a 10K resistor, and the input voltage, which is basically the output voltage of the power supply, is 3.3 volts DC. You can look up the reference voltage in the data sheet for this particular switch and power supply chip. It's 0.8 volts. The common mode voltage is the same. There's no external reference with the resistor divider, so the common mode and the reference are almost always the same, since most chips hook up their reference internally. To the right is the type of op amp. So we're using a transconductance op amp, and you can look in there, look in the data sheet, find the transconductance and the gain, open loop gain of the amp, and the bandwidth. And this will give you an output impedance of the op amp of about 2.3 mega ohms. Sometimes you have to calculate these out from what little information they give you on these error amplifiers and these switch mode chips. They put in these switch mode chips. Once you've got all this in, everything is pretty easy as far as loop compensation goes. Um, oh yeah, here's our error amplifier types that I discussed earlier. I selected a type 2, which is this one. It gives you the minimum amount of phase or phase lead. If you want more, you have to use a type 3. These are typically used with a voltage mode type switch mode power supply. Um, and I've already reviewed this part. And when you go, you can, I'll go back. Whoops. You could, once you're done with this part, you can hit compute component values, and that will bring you to this window. And then you can round. It'll give you exact values, and you can round these values off to the ones that you're actually going to use, and it will give you your first pole and first zero, the phase boost, the phase margin, and if you don't have enough phase boost, you would most likely get an error message down here telling you that you can't use this type of amplifier for the desired phase margin or crossover frequency that you're looking for. And after you're done with this page, you will, yeah, okay, I didn't even know. So after this page, you will go through several different other, it's pretty much it'll create a circuit model. Our software will create a circuit model of this op amp. Then then it'll do a circuit analysis, generate the data, and then you can import the data directly into the plot. So this is the synthesized error amplifier. And then I would go to our math menu and multiply data set 1 by data set 2 and tell it to plot that. And here is my predicted plot for this, and it's fairly close. It's almost 60 degrees. It's very close, and the frequency crossover's a little bit off, but a lot of that has to do with the rounding of the components. Um, and all you have to do is build that build that circuit and do a measurement and see if your predicted loop matches up with the actual loop that you have tested for. So I'll pause here. Are there any questions or comments? Okay, well, I'll keep going. So we'll go into our other major application of our instrument is to measure the input and output impedances of power supplies. Um, this is really important in distributed power systems, where if you could end up creating an oscillator by connecting up the wrong power supply or the wrong number of power supplies to a driving power supply. So this is like a simple diagram of what we did. I did do some testing for the ISS, so that's what we would do. We would test the source and load impedances of the orbital recovery units, and they would build their model in Houston. I believe that's where they had it, and make sure that anything they added to the ISS wasn't going to cause it to oscillate and the power system to shut down. So yeah, this is sort of an explanation of what happens is that most most power supplies or switching power supplies are a they're a constant power device. So they act like incremental negative resistor, especially at low frequencies, and you can, that negative resistance can cancel out any type of damping that you may have in your circuit and cause it to oscillate. So this is like our criteria for source load. If the source and the load magnitudes are the same and the phases are 180 degrees out, you will get a negative impedance or negative resistance oscillator. And here's a picture of that. We actually went and created an input filter for a power supply and, you know, made it a high enough Q that it actually went unstable at this point where the red notch crosses the lower plot of the source power supply. The upper one is the power input of the power supply being driven with a filter on the front end of it. So it definitely does happen. If you try hard enough, you can make an oscillator out of that. We use two different types of injection methods for this. Typically, for smaller power supplies, yeah, I'd say mid-range power supplies, you can use voltage injection where a you're using a power amplifier to inject into a high saturation current secondary transformer in series with the high line, and then you use a current probe and two channel. Well, this is the three channels, so you can measure the source and the load at the same time. The voltage, of course, the connection should be right at the terminals, and then if you want to have to measure impedance, the arrow on the current probe should be pointing at the terminals. If it's pointing away, then your your impedance is 180 degrees out, so you have to add a negative sign in front of your transfer function to get the correct impedance. And as it says, this has, it's pretty good for, measuring between, say, 10 and 500 kilohertz. The bandwidth of the transformer, injection transformer, is usually what limits this type of method. The power amplifiers we have usually have even higher bandwidth than the transformer, the ones we're using these days. So, and it is limited. The current injection is probably a much better method. It would work at low, medium, and uh, high power supply system that'll work on it. There's no real low end limit on the frequency of measurement, and depending on how good your injection device is, you can go fairly high frequency, especially with just like a MOSFET with a resistor if you're injecting into a small power supply. And for very high power systems, it's about the only way you can really do this. And these, once you're up in the megawatt range, you basically have to inject a square wave using an IGBT into a high power water cooled resistor. It depends on what kind you're using, or a utility grade resistor as your load. And you won't burn up the IGBT. It's either full on or full off, but the injection method, the injection method does work. Even if you're using a square wave, you will still get the correct impedances. Sometimes you can find an electronic load you can modulate, so you don't have to build your own simple load, but usually the people in the Navy or the Air Force, if they need something like that, they build their own unit. Um, so here's the equipment list. So with us, we sell audio power amplifier, we sell transformers. Uh, you can gang these transformers in parallel so you can inject into a higher current than say 100 amp. You can you could parallel the secondaries so you can and you know I usually set the primaries in series, and you can inject into several hundred amps. So that's kind of a nice feature. Or you need a active device, electronic load for current injection. 2 or 3 channel FRA. 3 channels a luxury, but it saves a lot of measurement time if you can measure both the source and the load at the same time. I've only ever really used a DC current probe with the appropriate current rating. Usually it's like I forgot the Tektronix, AM503, and the newer type current probe amplifiers. Most of these current probes have to be terminated into a 50 ohm uh, load. I like using a scope because then I can watch the injection and look at the screen. So I will generally use the scope as my terminator for these type of measurements. There's the setup connections. Yeah. So at this point, this is set up to measure the load, without any inversion of the tran. If Let me go back. So no, it's not this one. Okay, that's current. This is the voltage. All right. So I think we've sort of gone through this before. This is the setup. I generally used my oscilloscope as my terminator for the current probe output. Um, and everything is pretty much the same. You're injecting on either side of the or secondary of the injection transformer. So you want to put your bleeds right up on the load and the source, and it doesn't matter so much with the current probe, but whatever I'm interested in, I usually put the current probe right up next to it when I'm doing these type of measurements. Current injection, it's about the same. Everything's about the same, except if you were using a 3 channel, you would use 2 current probes, um, because you're looking at the current on each side of this injection points. And it's the voltage channel that doesn't need to be, it can be in the middle. Usually I put it up to the item of interest, but so or you can just use 1 current probe, but you're going to have to do twice the measurements too. You're going to have to measure on each side of this injection point to get your impedance here. Yeah, I'd say the big issue usually is if it isn't the injection or how you're going to inject into the circuit, it's dealing with the current probes. I would choose the appropriate current probe. It's going to have to deal with the DC offset, so you're going to have to set your range so that the probe can handle that. It's going to have the entire DC offset, especially if you're looking at it with the scope. It's going to have to be in the proper range. Uh, yeah, verified termination of 50 ohms. If you're using a terminator, people burn them up. You should make sure they haven't burned the one up that you're using. Uh, like I say, generally look at the voltage and current waveforms on the oscilloscope. You can see if you're having a problem. Um, and I choose the current range that gives you 3 to 8 divisions on the scope. That's including the DC offset. Usually those current probe amplifiers got good dynamic range. They're pretty sensitive, so they'll still pick your signal up even if you are set at a higher range. Um, I adjust the DC level. I zero the probes. I don't degauss them, but I do zero the probes so I can see if I'm getting the correct DC offset in my oscilloscope. And the next thing to do is calculate the impedance or effective impedance of your current probe. It's basically acting as a uh, current transducer or a resistor, really. So, you have to at least in these, yeah, okay. Here's my setup for one of my measurements. So I have to put a negative sign. Whoops. Have to put a negative sign on this measurement since my current probe is pointing away from the terminals. And this one, the current probe is pointing at the terminal, so I don't have to have a negative sign in there. And then our sense, that's your current probe amplifier. You got to figure out what the effective resistance, like the old AM503 type current probes, every I believe you set your scope to 10 millivolts division, so that's the voltage, and then you you divide it by the current range, and that'll give you the effective resistance. And then the newer type of uh, amplifiers, such as the TCPA 300, they just have a few fixed ranges to use here. So if I was going to scale, here's a scale factor which you have to enter in the this data set properties window will open, or if it's on the old, this is an old version 5 software. The data set properties are on the bottom of the newer software. So you have to go down there and set the scale factor to 0.2 if you're measuring channel 2/1. And this is a similar, if you're going to use this setting, you would also use a 0.2. So these are pretty fixed. There's a lot more variation if you use the AM503. It has many more ranges. And if your current probe was pointing away from the terminal that you're measuring at, it would be negative 0.2. Um, and these are things that happen when you're doing these type of measurements. The DC offset is not zeroed correctly. You might have to re-zero. If you got an old current probe, you're going to have to re-zero it probably almost every time you make a measurement. You can overdrive, at least with transformers, you can overdrive them at low frequencies. Seen this happen. So you should that's why you should use a scope to monitor your injection. You can also underdrive a, a power system too, but usually the noise, you'll have really jagged, I call it noise. I don't know if that's a correct term for it, but you will have really noisy, jagged plots. They won't be smooth. And I will let you know that you're probably not injecting enough signal. Same with integration time. If you know, this the type of analyzer we use, we don't use sweep averaging. We just try to reject the uh, noise with one measurement. We don't like do a bunch of measurements and then try to average out the noise. So if you're in integration time, which is sort of the inverse of the bandwidth on a network analyzer, if your integration time is too short, your the notch, I'll call it the discrete Fourier transfer notch, will be too wide, and you'll start getting noise. If you want it to narrow out, you have to take more data and spend more time on each data point in the measurement for rejection. And I had problems, at least with ISS, with the input filtering on some of their units, had a lot of really high Q resonances. So you could get into a great deal of trouble if you injected too much signal. You know, you could over voltage or get a distorted measurement. And here's a picture of me overdriving the primary. As you could see, it's starting to saturate. It will eventually just completely short out if I increase the signal level. So the lower bandwidth of our transformers, most of these transformers are pretty, no matter who makes them, the the specifications are about the same. They're usually got a 250 kilohertz upper bandwidth and a 30 hertz lower bandwidth. Once you get below 30 hertz, if you start injecting more than, I think this setting was 10 volts. Once you start injecting more than a volt or two, you're going to get saturation. And the lower in frequency, the easier it is to saturate it. So eventually you get to the point where you can't make a really good measurement because it'll saturate. So that's usually between 5 and 10 hertz with this type of transformer. Um, and these are just a few example plots of measuring a power supply. You can see at low frequencies, the phase and the gain are looking a little bumpy or noisy, as I call it. They're not smooth. So, oops. Um, for the short integration time, you will get the same thing, maybe even worse. You'll pick up a lot more noise. Um, and if you adjust your integration time and your injection level correctly, you can get a nice smooth plot, which is what what you need to look for with this particular type of measurement. Oops, going the wrong way. Measurement technique. Well, I guess I'll tell you what little I know. I've never really done a conducted susceptibility to mill standard 461, I believe, or I think it's CS 101, which is called audio susceptibility, but is very similar to a power supply rejection ratio test setup. You're injecting on the input of the power supply. You can use current injection. You can use voltage injection. You can use with a transformer if you want to do it that way. And then you're measuring the disturbance on the input of the power supply and comparing it to disturbance on the output of the power supply. Of course, you want very little disturbance to propagate through your power supply, and usually de-rejection is good inside the loop bandwidth. You usually get pretty good noise rejection. The loop will reject noise. This is for a LDO, but you could also use a switching power supply. Get the same measurement. They just call it audio susceptibility when it's a switching power supply, but it's the same principle. And then when you get to bill standard 461, CS 101, I think is what they call that particular section of that test. The test runs from like 30 hertz to 150 kilohertz. Uh, when you're when you're in when you're injecting into the load, I believe they want you to calibrate how much power you're putting in, and which I believe is now 80 watts into a half ohm resistor. So you have to compare your injection level into that resistor, and then at a certain frequency, and then try it on the unit at that frequency, all the way up to 150 kilohertz. So they want you to inject a certain power level, but yeah, I mean, don't think it makes that much sense, but that's their standard. It's like 80 watts till you reach 5 kilohertz, and then it rolls off to like 90 milliwatts at 150 kilohertz as the minimum. That's a minimum line. You can go above that line when you're doing an injection. Um, and that's probably all I know about that. It's like I said, I've never done it. Some people use a voltage instead. If you do 80 watt voltage into a half ohm load, I believe it's like 6.32 volts RMS power injection level. A lot of it depends on how much power your power amplifier. The ones we use can put out about 500 watts. They usually I don't think they would have any problem with that test. It's, are you injecting too much? They're very vague on that. So I guess that wraps it up. If anybody's got any questions or comments, let me know.
Yes, I had a question.
Sure.
On one of your slide, you were saying like before a test, do not degauss the probe before doing a measurement.
Yeah.
So is there any specific reason